So this is the last lecture. What I want to talk about a little bit is what are the questions that people are asking. So I'll spend most of the lecture talking about this. And then at the very end, I'll try to talk about the neutrino mass puzzle. So hopefully I'll get there. If I don't get there, I will have a lot of information on that on my slides, so you can look at that later on. So this is where we stopped, maybe the last time. Yeah, this is where we stopped the last time. So I was just giving you a picture of everything that we've learned about neutrinos. So we know that there are 3 of them. We've measured the 2 independent differences of masses squared. We've also measured all of the mixing angles. And we've identified what are the things about neutrinos that we haven't measured yet. And that's this list on the right-hand side. And we talked about that before. What I want to tell you about a little bit is how do we think we're going to get the answers to some of these questions. And I won't talk about this in a lot of detail, but I want to give you a flavor of what those questions are and how we think we're going to get an answer. And I'll mention that's not a comprehensive list of how we're going to get the answer, but it gives you a flavor of what the experiments are talking about. And I think Stefan talked about that. He'll probably talk about that next week as well. So the first big question that's very easy to understand is, as I said, we have 3 neutrinos. We know the differences of the masses squared, and that allows us to draw 2 different pictures of how the neutrino masses are ordered. And sometimes people refer to this as the 2 different hierarchies for the masses, or some people just call that the ordering. And it doesn't matter, it's just a name. But the idea is we don't know which one of those 2 pictures is correct. So I want to say something very obvious first. Those 2 pictures are different. They are not the same. Okay? So this is a real question. So it's, it's a physics question. You have 2 distinct logical possibilities for how the masses are ordered, and there is an answer. And the first question you should ask is, how come we don't know the answer? And you already know why we don't know the answer, or you might have thought about this already yourself. The reason we don't know the answer is because our measurements have not been precise enough yet. Yeah. Yeah. It's always, so for the normal hierarchy, it goes 1, 2, 3. And for the inverted hierarchy, it's 3, 1, 2. Oh, very good. So what was measured with atmospheric is this one or the other one. It was actually both. So that's the important part. When you do the atmospheric measurements, this number is too small. So those 2 delta m squares kind of merge into 1. So that's the idea. Now imagine that you were sitting all the way in the back of the room and you didn't have your glasses on. If you were looking at this picture, you would see this very big splitting here, but you wouldn't be able to tell that there's a splitting over there. So that's how the atmospheric neutrinos look. They don't have enough resolution to notice that those 2 states have different masses. So they just see the combined effect of those 2, delta m squared 3, 1 and delta m squared 3, 2. So they see an effective delta m squared, which is a combination of those 2. So yeah, that's a very good question. And that's what I wanted to try to say here. But that's the key point. The fact is, all of the experiments that we've done so far, they have never been able to tell in the same experiment that you have 3 neutrinos with 3 different masses. They can only see one of the 2 delta m squares at one time. That's not a fundamental physics fact. It's an experimental fact. So in fundamental physics, you can certainly know that there are 3, but every time you do an experiment, you don't get to see that. And this is kind of an accident. If the numbers had been such that all of the mass differences had been similar, then you would have been able to see all of them. And then that problem would not have been there. The other question you can ask, and this is also what's in the slide here, is what about the solar neutrinos? Why don't they get to see the large delta m squared? Because after all, it's large, so seeing a bigger effect is easier, except for the fact that these experiments are done with electron neutrinos. And the electron neutrino fraction of neutrino number 3 is very small. So if that fraction had been 0, then the electron neutrino would be blind to the existence of this other delta m squared, and the electron neutrino would only see the 1-2 system. So as long as your experiment is not very precise, you don't get to see the fact that the neutrino number 3 has a small electron component. And actually, it took us a long time to establish that the electron component was not 0. So that means that for a long time, all experiments that had something to do with electrons would only give us information about the 1-2 system. So again, these are the two coincidences that happen. One is that because UE3 is very small, electron neutrinos only got to see one mass square difference. And because delta m squared 1-2 is very small compared with 1-3, experiments with muon neutrinos only got to see the large delta m squared, and they never noticed the other delta m squared. On the other hand, the fact that this happened is good because you can learn a lot just by studying two-flavor oscillations. So the two-flavor oscillations capture most of the physics of the experiment, and the three-flavor effects are small. This is kind of what I wrote down here. Because it turns out that this ratio of delta m squares is small, and one of the entries in the mixing matrix is small, two-flavor effects are often a good description of everything. On the flip side, we can't know what the mass hierarchy is. So in order to violate that, in order to be able to tell which mass hierarchy you have to violate all of these approximations that happen in the experiments. And that's what we're doing now. So these are the experiments that are ongoing right now. They are designed to have enough sensitivity to get around the problem. Now, the way we're actually thinking about resolving this mass hierarchy problem relies heavily on matter effects. Okay, so it's related with noticing that theta 1-3 squared is not 0. That's kind of a condition number 1, but it turns out to be not sufficient. So the way we're going to do it, or the way, say, the NOVA experiment is going to do it, is to look at nu mu to nu e oscillations, but looking at the large oscillation frequency, the delta m squared 3-1. So I want to have conditions where I can see the delta m squared 3-1 very well, and I want to remember that theta 1-3 is small, but it's not 0. So if I can see that, I can get started. And my oscillation probability kind of looks like this. This statement is not necessarily true, but let's pretend it's true for this pedagogical purposes. So this is what this probability looks like, and you notice that if you stare at this, you can't measure the mass hierarchy this way either. And the mass hierarchy, remember I said, it's roughly equivalent to flipping the sign of delta m squared 3-1 into minus delta m squared 3-1. If you look at this expression here, if I change the sign of delta m squared 3-1, because the function goes like sine squared, nothing changes. So I don't get to see anything. The key point here is that this is the oscillation probability in vacuum. If I do these oscillations in matter, I have to take the matter effects into account. And we talked about this before. If I do this in matter, approximately my formula changes, where instead of having this mixing angle theta 1-3 and the delta m squared 1-3 in my oscillation frequency there, I have these effective angles, and the effective angle is proportional to this object over here, which goes like a delta m squared. This is supposed to be 3-1, so that's okay. Delta m squared 3-1 over 2e cosine of 2 theta 1-3 minus a. A is the matter potential. And cosine of 2 theta 1-3, theta 1-3 is very small, so cosine of 2 theta 1-3 is close to 1. And this object here goes like delta m squared 1-3. So if delta m squared 1-3 is positive, those two numbers will subtract. And if delta m squared 1-3 is negative, the magnitudes of those two numbers will add. So now you see that if delta m squared changes sign, my oscillations probability will change. So I'll show you the same picture that I showed you before, except of course that now, the way you want to read this is to say, if I do the experiment in vacuum, this is what my oscillation probability looks like. If I do my experiment in matter, and the hierarchy is normal, my oscillation probability will look like the blue curve. And if the hierarchy is inverted, the oscillation probability will look like the black curve. So by doing this experiment in matter, I can see what the delta m squared 1,3, whether delta m squared 1,3 is a positive or negative number. So that's the experiment that we want to do. Now, to do this in practice, you need lots of different things to happen. You need this theta 1,3 to be not 0, because if it were 0, then this curves would look like that, except that this number here would be really small, so you're not seeing anything. So nothing, if nothing changes, you can't tell that it changed, because it's still nothing. Okay? There's another issue, of course, is that when I draw this plot, the contrast, requires that you want delta m squared 1,3 over E to be of order your matter potential. If the matter potential is too small, this effect is really small, so that doesn't help. And I will leave you to think about this. If you're in the opposite regime where the matter potential is too large, it doesn't help either. So you have to be in a regime where the matter potential and the delta m squared over E are about the same. Okay? Now, the matter potential is proportional to the Earth's density. When you do the experiment, you can't change that. So the Earth's density is what it is. So that means you have to pick the right, because we know the delta m squared, you have to pick the right energy to get a big enough effect. Okay? So we do that. But, of course, the oscillation length itself depends on the energy. So if you have to pick a certain energy, in order for you to see something, that means you have to go far away enough to see any oscillation at all. Okay? So in some sense, the way the logic goes is that you know the matter potential, you want the matter potential to be of order delta m squared over E. That tells you what E is supposed to be. And then once you know what E is supposed to be, you also figure out what the baseline has to be for you to see an oscillation at all. And again, this is related to the fact that you don't want to be doing the experiment over here where the L is too small. You could do it all the way out here if you wanted to, but that's bad because the number of events falls off like 1 over the distance squared. So doing experiments further away is bad. So let's not talk about that. So that's kind of what people talk about in order to do these types of experiments. And when you go to a seminar, the language people will often use is to say that if you want to see the matter effects, you need your baseline to be long. Okay? And that statement is correct, but the reasoning comes because of the energy. So you want the matter potential to be of order the delta m squared over E. That means your energy has to be large, which means that your baseline has to be large to see any effect. So this is, for example, what the NOVA experiment is designed for, is to be in a regime where they can see this effect. Now, of course, there's another important thing to think about, which is the only reason I can make these figures to look very different is because I know what theta 1,3 is. If I didn't know the value of theta 1,3, by making theta 1,3, by making the angle bigger or larger, I can mimic this effect approximately. So let's say that I had this curve, the blue curve here, but if I made the amplitude of the oscillation smaller, I could make it be artificially as high as the black curve. I wouldn't be able to adjust the frequency, but the frequency is less important. The amplitude is very important. So knowing the mixing angle is very important. And you can do that in a variety of ways. You either measure it somewhere else, or if you repeat the experiment with neutrinos and antineutrinos, the neutrinos go like the blue curve and the antineutrinos go like the black curve, because the matter potential changes for a certain mass hierarchy. If you flip the mass hierarchy, it goes the other way around. So by comparing neutrinos and antineutrinos and seeing which one is amplified and which one is reduced, you can tell the mass hierarchy as well. Okay, so that's the strategy, and that's the only one I'll talk about here. So let me talk about, Zoom can do this ridiculously well. So Stefan also talked about that yesterday, yes. And the reason they don't overemphasize that, or maybe they do, but the reason they didn't talk about that too much is because we are semi-confident that by the time the Dune experiment starts running, we will know the mass hierarchy from the NOVA experiment combined with the other experiments that are currently taking data. So we are confident, in quotes, that we're going to know the mass hierarchy by then. We never know because we haven't done the experiments yet, but the data point to a direction where we think we're going to be confident that we will know the mass hierarchy. That will reduce the number of plots we have to make in a paper by a factor of 2, because we only have to make one hypothesis. So you should look forward to that. Let me talk about CP violation. CP violation is a really big deal in particle physics, and I want to try to convince you why this is an important measurement in a certain way. And we already talked about in the questions the leptogenesis issue and generating the matter-antimatter symmetry of the universe. I do want to look at this from a very particle physics-centric point of view, and I want to remind you about CP violation in the standard model of particle physics. And I will assume you've heard about this. If you haven't, then this won't be very interesting. So this is the idea. We have observed CP violation in nature, in the laboratory. Okay, there's a bunch of phenomena, and this list here is supposed to remind you of what those phenomena are. They have to do with precision measurements in kaon physics, precision measurements in B0 physics, precision measurements in, B sub S mixing, and so on. There's a lot of different types of experiments that have observed that CP is violated in nature. Indeed, one of the Nobel Prizes for particle physics is for observing CP violation in nature. What's really exciting is the fact that all of these phenomena are explained by one parameter in the Lagrangian. The same parameter, which is a phase in the quark mixing matrix. Okay? So there's only one parameter in the Lagrangian that describes all of these different phenomena. And we get very excited by the fact that we now have an opportunity to see at least one more parameter. And that should govern a lot of different phenomena that we haven't seen yet. And it probably has nothing to do with these other phenomena that happen in the quark sector. So that's one issue about CP violation in the lepton sector, is that because neutrinos have mass, there can be a new source of CP violation. So we want to know what that source is. And I also want to go back to this issue of CP violation again in the Lagrangian, just to say that this is a phenomenon that we don't understand, although it's kind of a philosophical question, which is the following. When you write down, so the model of particle physics is a very powerful model because it allows you to say many things in very general terms. So for example, if you didn't know that there was a third generation of particles, and you only knew about 2 of them, and you knew about all of the interactions in the standard model of particle physics, you could deduce, without making any measurements, that CP violation is not possible. Okay, so the standard model, there's a caveat to that, which I'll remind you of in just a second. Everything that you learn about the standard model, if you throw out the third generation, allows you to conclude that there's no CP violation in nature, period. Okay? So the observation of CP violation is a sign that the 2-flavor standard model is wrong. And of course, the solution to that is a 3-flavor standard model, and that can accommodate CP violation. I'm actually lying, and I'll tell you what the lie is if you now do the exercise in reverse. So we know the standard model has 3 flavors, and then you write down the Lagrangian, and then you ask, and you forget about neutrino masses. So you ask, in how many different ways can I violate CP, given everything we know about the standard model? The answer is 2 ways. And when I say 2 ways, I mean how many independent numbers govern CP violation. And the Lagrangian of the standard model tells you that there are 2 independent parameters that can do that. One is the phase in the quark mixing matrix. It's called the CKM matrix. So that phase governs a lot of the CP violating phenomena that we observe. It turns out that there's another CP violating parameter in the Lagrangian. It's called the Theta Qcd. And it's a term in your Lagrangian that you can write down, and it violates CP. And this number theta is an angle. You can write it as an angle. This is one thing that you often don't hear about in your particle physics class or your quantum field theory class. And you don't hear about it for a couple of reasons. One is that it's hard to explain, so it takes a long time to get there. The other reason is that we're kind of embarrassed by this number. What happens is this is an angle, and as far as all experiments we've ever done to date are concerned, this angle is exactly 0. And we don't understand that. So we invent some reasons, and there's some really nice models that explain that might have something to do with dark matter, but I'm not going to talk about that at all. But so basically, going back in the standard model, there are two numbers. One is this phase in the CKM matrix. The other one is this theta parameter. One of those numbers is, so the one in the CKM matrix is like 70 degrees. It's a big number. It's almost a 90-degree angle. The other one, this one, Theta Qcd, we know it's less than 10 to the minus 10. So when I say it's 0, it's really, really small. And we have no idea where these numbers come from. We think that they're not related at all. And we think we have a good reason to explain why this angle is 0. But we have no experimental confirmation of that reason. So now we learn that neutrinos have mass. And all of a sudden, the number of CP violating parameters more than doubles. So if the neutrinos are around a fermion, the number of new CP violating parameters is actually 3 more than the 2 that we started with. So we can violate CP twice as much as we could before because the number of parameters is much larger. That's also not true, but you get the spirit. So there are all these new opportunities for violating CP. So if understanding about the nature of CP violation is the thing that you're really excited about, the leptons contain, if you want, most of the information. And we've never gotten to see that information until today because we didn't know that information existed to begin with. Yeah. Yeah, so so when you write down your Lagrangian for QCD, you write down what's called the gluon kinetic energy. And that's written in terms of the gluon field strength, and it's proportional to the trace of G mu nu. Now, it turns out that there's another Lorentz invariant quantity you can write down, which instead of being trace of G mu nu, it looks like a trace of epsilon mu nu alpha beta G mu nu G alpha beta. Also written out in this way. So trace of a GG dual. And that's totally fine. It's Lorentz invariant. Blah, 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 all kinds of nice things happen. Now, when you're doing quantum field theory at a certain level, that term turns out to be a total derivative. And as you learned, total derivatives in your Lagrangian are not physical. They don't show up, right, in your action. And that statement turns out to be false because there's an assumption that goes into getting rid of a total derivative that has to do with the behavior of your fields at infinity. And because the gluon field is very complicated, it can get twisted around at your boundary and it gives you a non-trivial effect. So it took people a long time to figure this out. And these are really smart people. So that's what Theta Qcd is. It's a new term in the Lagrangian that's allowed by Lorentz invariance that leads to observable effects in a relatively subtle way, which is why it takes longer to explain why that happens. So that's the bottom line for that. The photon has this term too, but it's not physical. For the photon, you don't need to write that down. Is that true? I think that's true. I mean, I'm sure it's not physical. I can't remember if you can write it down. I think you can write it down. But it's not physical, so why would you? But the other thing I want to say with this slide is this is something that people often talk about when you say, oh, I want to measure CP violation in the neutrino sector because these are parameters we've never measured before. Then many people would just they'll be kind of bored and say, oh, but we know that CP violation in the quark sector is really large, and CP violation can happen in the neutrino sector, so it's probably also kind of large, and it's some random number, and nobody cares what it is. That's kind of some people will complain that way. But I do want to remind you that we have no idea if that statement is true or not. So that's why we do experiments. People have a lot of prejudices about what the answer will be, but there's no substitute for actually finding out what the real answer is, as opposed to what people think the answer would be. And I do want to point out that out of the two parameters that we have measured, one is really large and the other one is really big. So if you want to guess what the third one will be, the amount of information you have access to is very limited. And the last thing which I wrote down over here is a historical fact which I did not mention, which is this is a very important lesson for younger people. So I told you about this thing called the solar neutrino puzzle and the atmospheric neutrino puzzle. And when these puzzles were getting started, people thought that maybe neutrino oscillations was the answer to the puzzle. And nobody believed those answers to zeroth order. Okay? Now, why was that? Especially for the, for the solar neutrinos, it's a more complicated story. For the atmospheric neutrinos, the results that first came out were quite strong. They had like 3 sigma evidence that the muon neutrinos going through the Earth were disappearing. And people said, maybe that's neutrino oscillations. And nobody believed that. I mean, if you ask your older professors, they will probably lie, but they didn't believe it at the time because nobody did. Now, why didn't anybody believe that? Because in order to explain the phenomenon, you needed a mixing angle that was like 45 degrees or 50 degrees. And nobody could envision an angle that was 45 degrees because that was too large. All of the mixing angles we knew about from the quark matrix were very small. So when people postulated that, oh, maybe the neutrinos have mixing, that's okay. That's not very strange. But nobody could conceive of the idea that the mixing angle could be 45 degrees. That made no sense. I mean, somebody told me once he was in a seminar by Hans Bethe, who's a very famous, very, very famous physicist who did all kinds of really amazing things. And then somebody asked him about, what about the atmospheric neutrinos? He was talking about neutrino oscillations for solar neutrinos, where you could solve the problem with a small mixing angle. And then somebody asked me, how about the atmospheric neutrino puzzle? Is that neutrino oscillations? And then Bethe said, oh, no, that's not true because mixing angles are small. And of course, there's no evidence that that's a theorem, but that was completely based on prejudice and based on just one data point. So we are really good at taking one data point, transforming that into reality, and using that as a theorem as guidance for physics. Sometimes that works, sometimes it does not work at all. Okay, so I'll very quickly remind you of how that works. I think that was a homework problem. The way that we're going to see CP violation is to look at the oscillation of muon neutrinos into electron neutrinos, compare that with muon antineutrinos into electron antineutrinos. Here are the amplitudes for these two processes using the language of neutrino oscillations that we've been talking about. And I'm not going to go through how you get this, but the important question you have to ask yourself is, this is a complex number. This is a different complex number. CP violation is related to the question as to, can this complex number here be different from that complex number there? So in magnitude. They're clearly different complex numbers. We don't care about that. We want to know if their magnitudes are the same. And that tells you how you do your experiment and what it takes to see CP violation. And I'm not going to go through the exercise, but I'll let you look at it. There are many, many conditions that have to be met for CP violation to exist, period. One is, you notice that these amplitudes have two terms in them, right? They are the sum of two terms, the way I wrote it. You can convince yourself that if either one of those terms is 0, there's no CP violation. So in order for the magnitude squared of this number to not be the same as the magnitude squared of that number, it better be that there are these two terms and that none of them are 0. Okay? Again, this is a statement about complex numbers. You can quickly convince yourself that that's true. What does this mean in terms of physics? What it means is that if any of these elements of the mixing matrix are 0, there's no CP violation. Because then I only get one term and not both. Another thing it means in terms of physics is, if you look at this object here inside of the little parentheses, that's where the delta m squared piece is. So if one of these delta m squares is 0, then one of those terms will vanish. So let's say delta m squared 1, 2 is 0. This thing in the parentheses becomes 0. And then again, you only have one term, so there's no CP violation either. In practice, that means you have to do an experiment where both of these exponentials are not equal to 1, that means you need a long baseline. And you need to see, in many quotes, both delta m squares. If one of the delta m squares is 0 for your experiment, you don't get the CCP violation period. And then, of course, the last thing that's required, of course, is that these u's have to be complex numbers. If all the u's are real numbers, then actually this complex number is the same as that complex number, and you don't get CP violation either. So this is what it takes to do the experiment. Some of it we can control by controlling the conditions of the experiment itself. Some of it relies on us getting lucky. And so far we've gotten very lucky, except that we don't know what delta is, and that's the thing we're trying to measure. And I will say that in order to do this for real, it's actually very hard. And I'm not going to talk about this at all. One of the main concerns people worry about are matter effects. So remember, matter effects make neutrinos and antineutrinos oscillate differently. CP violation also makes neutrinos and antineutrinos oscillate differently. How do you tell the difference? And that requires that your experiments have access to enough information to make this choice. You know, in order to decide if the neutrinos and antineutrinos are acting differently because of the matter effects or because of the CP violation or both. And disentangling these two different effects is part of the goals for doing these experiments. Okay, so enough about oscillations. I want to go very briefly through other stuff that we don't know about neutrinos. The first one is something we have talked about, which is we've measured the differences of the neutrino masses squared, but we don't know what the neutrino masses themselves are. Oftentimes people will pose this question in the sense of asking what's the mass of the lightest neutrino? Because if I know the mass of any neutrino, because I know the differences of the masses, I can figure out everybody else's mass, especially if I know the mass ordering as well. And again, this is a very important physics question. It has an answer, but you can't get the answer by doing oscillation experiments because they only measure the differences of the masses squared. So you need to go outside of neutrino physics for that. I mean, outside of neutrino oscillation physics for that. And we've already talked a little bit about how to do that. Stefan will talk about this next week. One way to see neutrino masses is by using kinematics. So if you do a measurement of a neutrino process or a process that involves neutrinos really, really precisely, and the neutrino has a non-zero mass, it should leave an imprint in the kinematics of your process. And the best way to do that we have identified is by studying beta decay. And in particular, people talk about tritium beta decay. So tritium is the thing that we think we can measure the beta decay spectrum the best. There are lots of reasons for choosing tritium. One is that you can get lots of it and it's not super duper expensive. So that's always nice. The other one is the way that you measure this is by measuring the spectrum, and you want to measure the end of the spectrum, and the smaller the endpoint energy of the spectrum is, the bigger the effect is, relatively speaking. So you want an atom that has an endpoint of the decay spectrum to have a very small energy. Okay? So that's related to what's called the Q value of the decay, which is how much energy is available after you transform your tritium into a different nucleus, how much energy is available for the electron neutrino system. So you want an element with a small Q value. And again, Stefan will probably talk about this. There is, of course, a caveat, which is the smaller the Q value is, the longer the lifetime is as well. So if you find an element with a really, really tiny Q value, you can in principle measure the lifetime, you can measure the neutrino mass more easily, except that the nucleus never decays. So you can't do the experiment because there's nothing to see. Or the lifetime is like 100 million years. So you don't get enough events to do the experiment. So tritium is a nice choice in the middle. Again, Stefan will talk about this. This is a really hard measurement, and I'll tell you how you do it. So here's what the beta spectrum looks like. You can zoom into the endpoint, and if the neutrino mass is 0, this is this effective electron neutrino mass that I talked about yesterday in the questions. So if the effective neutrino mass is 0, this is how the spectrum ends. If the effective neutrino mass were 1 electron volt, this is how the spectrum would end. And your job as the experimentalist is to tell the red spectrum from the blue spectrum. The only thing I want to say about this, which is very important, especially if you're a theorist, is that the way that you're going to measure this is not what you think. Okay? So when people talk about this, they often say that you want to measure where the spectrum ends. And if the spectrum ends here, the mass is very small. And if the spectrum ends 1 electron volt to the left, then you would know that the mass is 1 electron volt. That's not how you do the measurement. The reason is you don't know the position of where the spectrum ends that well anyway. So you can't measure that. But what you can measure is the shape of how the spectrum ends. So the shape of this spectrum is different from the shape of this spectrum. So you're actually making a shape measurement. And as all the experimentalists here know, measuring the shape of something is way easier than making an absolute measurement of anything, because the shape is robust and it doesn't care too much about how poorly or how well you know certain things. Absolute measurements are really hard. Okay, so a shape measurement is kind of like a relative measurement. So this is how they're going to do this measurement. One thing that is included in this picture, and again, Stefan will talk about this. This plot here is done in arbitrary units, not astronomical units, by the way. This is arbitrary units. And this is the endpoint of that. What this number here represents is the fraction of your decays that lives here. So out of all of your beta decays, 2 times 10 to the minus 13 are the electrons you care about. You don't care about all the rest of the 10 to the 13 of them. That means 2 things. One is that you need lots of tritium, because it's very rare that this will happen. And of course, the other one is you better not do anything wrong. Because if you mismeasure the energy of one of these guys, and it happens to show up in the wrong place, there are 10 to the 13 of those that can do something wrong. So you can't do anything wrong at that level, which makes the measurement very, very hard. And again, yeah. That's right, yeah. So the answer is, in principle, you could see the effect of all 3 masses, because what you measure, if you want, is a spectrum that's a combination of 3 spectra that look like this, but they all end at different places, and they're all weighted by the elements of the mixing angle squared. Yeah, so the spectrum that you see in a perfect world is kind of a spectrum that does this. Yeah, so this is how the spectrum really would look like. And the relative weights of these different contributions are proportional to UE1 squared, UE2 squared, and UE3 squared. Now, this is in a perfect world. In a less than perfect world, these kinks here are not visible because they all happen over here. So what you really see is a combined, imagine now that you added a really, really big curve there, and you kind of only get to see a combined effect of that, and that's why you only have sensitivity to one number, and that's why you don't really care about the mass ordering. Okay, so that's the tritium beta decay experiments. I'll let Stefan tell you about how we're going to do that, so I'll skip that part. The other thing, which I will also not say very much, another piece of information about neutrino masses comes from cosmology. We've also talked about this. This is related to the fact that the neutrinos are not the dark matter, but if they were the dark matter, they would be the wrong kind of dark matter. So by making sure you don't have too much hot dark matter, you can constrain the neutrino masses to be less than something. Again, that's not the whole story, but it's one way to think about the story. And it's an effective way of doing that. And I have a bunch of old plots, which I won't go through, but right now, if you look at cosmological data, they want the neutrino masses to be less than some fraction of an electron volt. And the object that they constrain is the sum of the masses. So they will say, we want the sum of the masses of the neutrinos to be less than something. And that something right now is about 0.2 electron volts, depending on who you ask. Or actually, it depends on which data sets you decide to combine and which assumptions you choose to make and how strongly you believe other things and so on. So the answer is very dependent on your cosmological assumptions. And all the assumptions are very reasonable, but you can play with them to get around some of the bounds. And I don't want to talk more about that, because I do want to talk about a different question, which is a more complicated question. And I do want to spend a little bit of time talking about this. So, there's a lot of measurements we want to do that have to do with neutrino oscillations and understanding whether we're leaving out ingredients from the picture and whether we've established all the numbers in the picture very well. Then I said the other thing we would like to know about neutrinos is what their masses are, because we only measure the differences of the masses. So the third thing we want to know about neutrinos is, are they Dirac or Majorana fermions? And I will try to reword the question in a way that hopefully makes sense. And this is related with the following fact, which is, the easy way to talk about this is the following. You look at the neutrinos, unlike all of the other fermions in the standard model, fundamental fermions, they are the only ones that don't have any electric charge. So it is a logical possibility, because they don't have any electric charge, that the neutrino and the antineutrino are the same particle, that the neutrino is its own antiparticle. And that's the way people talk about that. And I will say that that's a totally reasonable way of talking about that. But it's just, but it's confusing. But I will say that even though this idea sounds, for some people, very disturbing, it shouldn't be. We know of many particles that are self-conjugate. This includes some of your favorite particles. So the photon, for example, is its own antiparticle. There's no antiphoton. And I bet you never worried about that, but it's true. There's no antiphoton. The Higgs boson is its own antiparticle, it turns out. Yes, that's true. The Higgs field is a different story, but the Higgs boson is. And the neutral pion is its own antiparticle. The pi naught, which decays to 2 photons, that's also a self-conjugate particle. And again, these are all these are all bosons. The photon is a spin 1 particle, and the Higgs and the pi naught are spin 0 particles, and they're all happily their own antiparticles. Now, what I do want to remind you of is the fact that even though the photon is its own antiparticle, it has 2 independent states in it, which are labeled by their polarizations. So if I want to describe a photon state, I can have a right polarized photon and a left polarized photon. And these are different things, right? One has one polarization, the other one has the other polarization. And they're 2 independent things. Okay? And nobody gets confused about that. One is not the antiparticle of the other or anything like that. They are just 2 different photon states. Okay, so let's talk about neutrinos now. And the end of the day message will be similar to what I've just said about photons, which is, right now, we know of 2 neutrino states when we remember that neutrinos are fermions. And when you have a fermion, you also get to have 2 independent polarizations. You can either be left-handed or right-handed. If you don't like left and right, you can be spin up or spin down, for example, right? So a spin up thing is not the same as a spin down thing. Okay, so hopefully that's clear. And as far as the neutrinos are concerned, we've only seen 2 states of neutrinos. There's a left-handed one, and there's a right-handed one. The left-handed one we call a neutrino, and the right-handed one we call an antineutrino. But that's just the names that we gave to those 2 objects. We do know that those 2 objects exist, okay? And that's why they could be their own antiparticle, but they're still 2 independent objects. So you would never confuse the left-handed thing with respect to the right-handed thing, because they're 2 different objects, even if they were particle-antiparticle, even if they were the same particle. Okay? Let me try to say this in a slightly different way by talking about the electron. And I'll try to remind you of everything that we know about the electron, given the Dirac equation or quantum field theory. So imagine that you had never seen an electron before, but all of a sudden you make a measurement and you discover an electron, and you figure out that the electron is a left-handed fermion. Okay, so that's this object up here. So if you know nothing about this electron that you've just discovered, you know about the CPT theorem. So you know for a fact that if you ever observe this left-handed object here, there must be another object which is right-handed and has the opposite charge as that one by the CPT theorem. That is not optional. Okay? So is everybody fine with that? Again, I don't have to assume anything except that quantum field theory is a thing. Okay? Now, if I make more measurements with my electron that I've just discovered, I will figure out it has a mass. And once I have made that discovery, I can immediately conclude that there has to be another degree of freedom, which is a right-handed electron. Okay, how do I know that? Because that's equivalent to saying that you go in the rest frame of the electron and you observe that you can see the electron would spin up. And I'm just saying that if you see an electron would spin up, you can deduce that there must be an electron would spin down. It would not be possible to live in a world where all electrons had spin up. Because in that world, that would mean that the up direction is super special. And clearly it's not, because I can turn upside down and everything that's up becomes down, and I can still describe all of physics that way. So because there's no preferred reference frame, if I ever see an electron with a spin up, there has to be an electron with a spin down. And in this helicity language, the left-handed electron implies the existence of a right-handed electron. That's related to this picture here. We don't care about this picture. And of course, the CPT theorem tells me then that if I have an electron that's right-handed, there has to be a positron that's left-handed. And the conclusion of all of this story is to say a massive electron implies the existence of 4 independent degrees of freedom. The right and left-handed electrons and the right and left-handed positrons. Okay? That's everything we can say about the electron just by observing one of them. Let's go to the neutrinos. So here we have the neutrinos. We've seen left-handed neutrinos. The CPT theorem says that there has to be right-handed CPT partners of these left-handed neutrinos. Those two states must exist by the CPT theorem. If the neutrino didn't have a mass, that's the end of the story. And this, by the way, is a very, very powerful statement, which is to say a massless fermion can exist with only the spin up component. You don't need to have the counterpart spin down. Now, how is that possible? That's possible because a massless fermion can't stop. So you can't stop to ask whether the spin is up or down. You can only talk about the direction of the spin relative to the momentum. And that object is actually Lorentz invariant. If the mass is 0, if your spin is aligned with the momentum, that will be true for any reference frame that you can think of. So you would never get confused. You would never get to a reference frame where the left-handed guy looks right-handed. Okay? That's true for photons, for example. Now, the neutrinos do have mass. That's what we've discovered. So if the neutrinos do have mass, I know that this left-handed object has, if you want, a mass partner. The equivalent, spin up and spin down. They have to both exist. And of course, if this guy exists, this other guy exists as well. Now, here's where I have a choice. All that I've deduced is there's a left-handed guy and a right-handed guy, and then there's a left-handed guy and a right-handed guy. Are these two brackets here the same or not? That's the question that I'm asking. And they could be the same. It is possible that the Lorentz partner of the left-handed neutrino is still the right-handed antineutrino. That's what it means to be a Majorana fermion. And the end result of this discussion is if you happen to be a Dirac fermion, you are described by 4 degrees of freedom. And if you're a Majorana fermion, you're only described by 2 degrees of freedom. There are fewer degrees of freedom around. Now, finally, I want to remind you of the fact that you could not have gone and gotten confused about the electron and asked that question. Okay? And the reason is the electron has charge. So it is not possible to ask whether the mass partner of the left-handed electron is the right-handed positron. Because that would be like asking you know, if I see an electron with a spin up and I do a rotation by 180 degrees, do I see a positron with spin down? The answer is no, you're crazy, right? Because you have charge. And the charge doesn't change when you do a Lorentz transformation, and the charge is conserved, so you would never confuse something with positive charge with something with a negative charge. They're not the same particle. The neutrino doesn't have charge, so you could have the possibility that they are the same. But if that possibility is true, the neutrino better not have charge. And when I say charge, I mean any charge. There cannot be any global quantum number that you can assign to the neutrino which is different from the quantum number of the antineutrino, because they are the same particle in that sense. They have the same quantum numbers, so they can't have any quantum number that changes from particle to antiparticle. Okay? So hopefully that's clear. So then this is the question that we're asking. It's a degrees of freedom question. So the question is, if I have a massive neutrino, do I describe it with 4 degrees of freedom or 2 degrees of freedom? Yeah. Yeah, so that's the key point, right? So they can't have lepton number either. So that's how you look for whether the neutrino is its own antiparticle, is that the neutrino seems to have a quantum number which is lepton number. So that better not be true. That has to be false. So you want to check if lepton number is conserved or not. Okay? So that's the question, yeah. We don't know whether lepton number is conserved or not. All the evidence we have access to today says that lepton number is conserved. It doesn't mean it's conserved, it just means that all the evidence we have amassed so far is consistent with lepton number being conserved, which is 2 very different statements. You can never prove, by the way, that lepton number is conserved. You can only prove that it's broken by seeing it be broken. But that's I'll mention that in a couple of minutes. Yeah. It's the same thing, yeah. You can write down a mass for the neutrino only with the left-handed field. So the left-handed field describes these 2 particles, and the right-handed field would describe these 2 particles. So again, another way of asking the same question is there a right-handed neutrino field? The answer is either yes or no. And of course, that field could exist, but it may have nothing to do with the neutrino mass. But we don't want to get into those details. But that's another way of asking the same question. And again, I don't have time. Understanding massive Majorana fermions is a thing. It's something which is fun to do. They obey a modified version of the Dirac equation, if you want to think. It's a constrained version of the Dirac equation, or you can write down it in a different basis, and you can write down the masses for these things, and you can see how you can write down what's called a Majorana mass for a Majorana fermion, and how a charged fermion cannot have what's called a Majorana mass. But I don't want to get into those details. But yeah, these are all interesting things. Yeah. Mm-hmm. That's a very good question. And the answer is that in spite of the fact that if the neutrino is a Majorana fermion, lepton number is not a good symmetry, lepton number is approximately a really good symmetry, even if the neutrino is a Majorana fermion. And that's why, you can argue, that's why we haven't seen any evidence for that yet. Okay? And I'll try to explain a little bit more of what the story is. Yeah. That's right. That's exactly correct. It's superhelicity suppressed, if that makes sense to you. Now, why don't we know the answer to this question? Why, and I like to say, this is a big, simple question. We're describing an object, and it either has 2 degrees of freedom or 4. 2 and 4 are totally different, right? We would not get confused between 2 and 4. But somehow we don't know the answer to that. And the key way of thinking about this is to remind yourself that if the neutrino mass had been 0, I would not be able to ask this question. It's not a question. It's not a physics question. A massless fermion, you can call it Dirac or Majorana, whatever you like, but it's not a physics question anymore. a massless Dirac fermion and a massless Majorana fermion, if you compare them in the right way, they are indistinguishable. Okay? Another way of saying this, if the electron mass were 0, the left-handed electron and the right-handed electron, they could still both exist, but they would be completely unrelated to one another. You would not call them, one of them electron, the other one electron. You would call them, Alice and Bob, and they would have nothing to do with each other. They would be completely unrelated. It's only because they have a mass that you can say that the right-handed electron and the left-handed electron are, in some sense, the same particle. If they didn't have a mass, that would not be true. So because you can only ask this question if the neutrino mass is not 0, and this is very important, if you can't ask the question, you better not be able to get an answer. Right? So if the question doesn't make sense, you better not get any meaningful answer to the question that you can't ask. So this means that if you can figure out a physics process that knows how to answer that question, the amplitude for that process better vanish exactly when the neutrino mass is 0. So any observable that you can think of that can tell whether the neutrino is Majorana or Dirac better vanish when the neutrino mass is exactly 0. And this is your problem, because the neutrino mass is not exactly 0, but it's really small. So any observable that will tell you whether the neutrino is Majorana or Dirac has a rate or an amplitude which is really, really tiny. And I do want to say one thing more about this, just to give you a sense of this helicity suppression that explains how this works out. So imagine that I have a physics process where an electron hits something and produces a neutrino. If I want to describe this neutrino in the lab frame where the neutrino energy is very large, and I want to use the helicity of that state, I would say that the electron neutrino is going to be mostly left-handed, but it has a tiny probability of having the wrong component. And that probability is proportional to the ratio of the mass and the energy of the neutrino. So that's my neutrino that now is going to come in and hit my detector. When it hits my detector, it can do one of two things. It can either hit as the left-handed guy, and then it does the normal thing. And it turns out that the left-handed object, regardless of whether the neutrino is Majorana or Dirac, really likes to produce electrons and not positrons. Now I have this right-handed object. Here's where I have a choice. If the neutrino is Dirac, the right-handed object doesn't interact with anybody for the most part. So if the neutrino chooses to behave as the right-handed object when it hits something, nothing happens. It does nothing. End of story. So you get a tiny suppression to your flux, if you want to think about it that way. Maybe that's not even, I think that's true. Okay. I have to double check that statement, so don't quote me on that one. But if the neutrino is a Majorana fermion, then the right-handed object is the thing that we normally call the antineutrino. And we know that that object that we like to call the antineutrino does know how to hit things, and it does like to produce positrons. So if my neutrino chooses to behave like the right-handed object and it hits something, then it will produce a positron. Now the probability for that to happen is going to be proportional to the probability that you saw the right-handed guy, which is this m over e squared. There's another contribution, by the way, of the left-handed guy choosing to behave like the right-handed guy because it has a mass. The amplitude for that is the same. So that the answer is proportional to this m over e squared. And this is what makes this experiment impossible to do, because you can plug in numbers. If you plug in, pion decay, the neutrino energy is of order 100 MeV, the neutrino mass is less than 0.1 electron volts, the probability for that to happen is 10 to the minus 18. There's no experiment you can do that will ever see that. So the way that we want to solve this problem is by doing the experiment which works. And here's another thing which is very powerful. When you have these really tiny probabilities, regular particle physics-like experiments always fail. And the reason is the luminosity is too small. So basically, if you wanted to do this experiment, you have to, you're producing pions with a beam. So that means you're shooting protons on a wall to produce pions. And you don't have enough protons, and you can't shoot them on the wall fast enough to produce enough pions. So the luminosity is very small. So the way around that is to get some place which has a lot of luminosity for free. And that's where nuclear physics comes in. If instead of shooting protons on a wall, I can just collect a lot of protons and let them do their thing by themselves, it's much easier. Because my luminosity, in quotes, is gigantic because I can get a lot of atoms. I don't have to shoot anybody on a wall. I just have to wait. Sometimes I have to wait a long time. But if I have to wait too long a time, I just get more stuff. And I just keep getting more stuff. And hopefully someday this will work out. The way to see this is to look for neutrinoless double beta decay. Stefan will also talk about that next week, he said. So I'm not going to dwell on this very much. The key thing, of course, is that if the neutrinos are Majorana fermion, the rate for neutrinoless double beta decay in the simplest scenario that you can think of is going to be proportional to what's called the effective neutrino mass for double beta decay. Sometimes that's referred to as m beta beta. Sometimes it's referred to as MEE. And that's a linear combination of neutrino masses. Okay, that particular one that I wrote there. And this is something we already knew, because I said that these processes have to vanish once the neutrino mass goes to 0. That means that the probability that this happens goes like the neutrino mass squared. And if you ask which neutrino mass goes there, the answer is all of them, and they go there with different weights. There's only one important point that I want to emphasize is these elements of the mixing matrix are complex numbers. And of course, the rate is proportional to the magnitude of that. But because we're adding 3 complex numbers, they can add up in some funny way. And it is possible for this rate to be 0. Even though the 3 different complex numbers that you're including in your sum are not 0, 3 complex numbers are allowed to add to 0. I bet you learn about this in your complex numbers, first year class or maybe high school class. But that's a thing, and that's what leads to your expected rate for double beta decay to be really, really tiny in a certain region of mass space. Because that's when the 3 complex numbers can add up to 0. And we don't know if that's happening or not. So I don't want to talk about this. So I have some slides that explain why we have Majorana phases, and I'm not going to talk about that because I want to talk about something else. So mostly what I'll try to do is just to pose the problem of neutrino masses, and then I'll stop. And then my slides will have some examples of how to address those problems. So in a nutshell, if you're a theorist and you don't really care about all these experiments that I spent 5 hours talking about, here's what we really care about. What we really care about is that neutrino masses are not 0. That's the big discovery. So that's the paradigm shifting discovery that happened 20 years ago, this year. Probably this month or maybe next month. And this is a really big deal because we didn't know that before. Now we can look at this in the bigger context of particle physics. So this thing on the left-hand side is a plot of all of the fundamental fermion masses that we know about. And the neutrino masses we don't know. So I've indicated them by arrows, and I assume that the mass hierarchy is normal. And I assume that the upper bound is very, very generous. I said it's about 1 electron volt. It's about 0.1 electron volt. So, but that doesn't change anything that I'll say later. So it's indicated by those arrows. Now, all of the charged fermion masses are up there, and we actually know those quite well. Even the light quark masses we know pretty well. Now, this is a really impressive plot for many, many reasons, and I'll highlight all of them because they're all very important. One is, in order to make this plot, you need something like 15 orders of magnitude. Okay? Because you're all associated to particle physics in some way or another, you don't appreciate how strange this statement is. Okay? And this is a really weird statement because basically we're saying that there is some object that weighs 200 times more than the proton That's a fundamental particle. Then there's this other object, which weighs 2,000 times less than the proton, and that's also a fundamental particle. And these are all fundamental particles, and they all have no size, and et cetera, but somehow their masses can change from, different, they can be different by 15 orders of magnitude. This clearly makes no sense. But there it is, that's life. The other thing which is also very important to appreciate is the fact that the charged fermion masses are also very different. They span up almost 6 orders of magnitude. The lightest fermion is everybody's favorite fermion, the electron, and the heaviest one is the top quark. And they do span, more than 5 orders of magnitude. And we have spent, a big chunk of the theoretical physics community, we spent a really long time trying to figure out why this happens. And we don't know why, but we've thought about it for a long time. Another feature of this which I want to point out is that in spite of the fact that this gap is very big, it is not very empty. So as you go up in mass, every order of magnitude or so, you run into some new fermion. Except for the top quark, which is more weird, but here's a 2 order of magnitude gap. All the other gaps are less than an order of magnitude. And by the way, the electron is a little bit weird too, but anyway. So this is also different. And again, this is very important for the history of particle physics, because as we were building better experiments and better accelerators, every once in a while we would discover some new particle. And that's because there was some new heavier particle to be discovered coming up. So basically, this starts out at the turn of the century all the way up to the late 1990s, which is nice. So we have about 100 years of doing better experiments and running into a new particle every decade or so. That's not true, but approximately. So now the neutrinos come in. The neutrino masses are not 0, but they're all the way down here. Okay? And the gap between the largest possible neutrino mass and the electron mass is more than 6 orders of magnitude. It is way bigger than the electron to top quark gap. On top of that, the mass region between the electron and the largest possible neutrino mass, as far as we can tell, is completely empty. There are no particles that live there. And none of these statements are scientifically compelling statements, but they all make for a very weird picture. And the real question then becomes, and this is a big driver in the community, is that the neutrino masses look wrong. They look like they don't fit in. A different way of saying this is that it looks as if the dynamical origin of the neutrino mass is qualitatively different from the dynamical origin of everybody else's mass. Now, if you compound that with the fact that the neutrinos can be Majorana fermions, the argument becomes even more compelling, because it says, hey, the neutrino is the only thing that could be a Majorana fermion. And if it were a Majorana fermion, they can't get a mass through the Higgs mechanism directly. So all of these things, this is not a scientific statement, but it's a very, very compelling statement that guides the theory for a very long time. If you don't like, yes? Oh, the colors mean nothing. It's just to guide the eye. If you like, the blue ones are the first generation particles. The green ones are second generation. The black ones are third generation. And by the way, this label here is wrong, I think. So this is it's not generation, it's something else. I have a fixed version of this plot, but clearly I didn't include it there. Okay, so the other thing that's very important is the masses themselves. So if you ask, and we've been talking about this in this a lot, if you ask yourself, what are the things that the standard model got wrong or did not take into account? We've been hearing about the dark matter, and we've been convinced by Fabio and Farinaldo that the dark matter cannot be a standard model particle. And you're all convinced by now. You should ask them about primordial black holes, by the way. That's a secret question. Farinaldo's not here, right? Oh, I'm sorry, you're here. Good. Okay, so yeah. It's not primordial black holes either, but that's harder to explain, right? So dark matter is not in the standard model. It's some new particle we don't know about. neutrino masses are in the same category of question. Is that if you look at the standard model, as you learned, neutrino masses are predicted to be exactly 0, and they're not. So something happened. And the simplest thing we can say is that there are missing degrees of freedom in the standard model that are responsible for the neutrinos getting a mass. That missing degree of freedom could just be a right-handed neutrino, and maybe the neutrino is a Dirac fermion. But nonetheless, it is a new degree of freedom about which we didn't know before. So it's a big deal discovery, and we don't actually know if that's the right answer or not. The answer could be much more interesting. And again, the other things we don't know complete this footnote here. So it's a really, really short list. So it's non-zero neutrino masses, dark matter, and people have already asked about this. There's this baryogenesis problem. That's a big deal particle physics problem, in my personal opinion. And then, of course, there's the accelerated expansion rate of the universe now. And if you're very ambitious, you can talk about inflation as well. And both of these two phenomena are things we don't understand. And we have many, many ideas for how they happen, at least the inflation part. The cosmological constant part, not so much. But we have no idea what the answer is. The only thing we can say is that the naive particle physics answer to that question is just totally wrong. So we don't even talk about that. I mean, the answer is so wrong that we know we're not asking the right question. I think that's the one way of putting it. And maybe this is a very fundamental physics that is outside of quantum field theory. Yep. To the cosmological constant problem. Now, it's a tricky question, and the answer is equally tricky, because the cosmological constant can be whatever it wants to be, and our model has no ability to predict what it is. That's the end of the story. Nonetheless, if you're very brave, you can try to predict it anyway. And then you get the answer wrong by 120 orders of magnitude. That clearly means that you are not properly equipped to try to get the answer. So that's the end of that. That's all I know about that. Many people are much smarter than me, and they have much bolder answers to the problem. But whatever it is, the standard model particle physics has no ability of doing inflation, for example. Is that true? I think there used to be Higgs inflation, but I think it's not allowed anymore. Okay, good. So that statement is true. So that's the other thing that's very important. So I already talked about that. And I think I'll stop probably with this slide, and then I'll jump to the conclusions, and I'll let you look at how can neutrinos get a mass discussion, which I did not have any hopes of getting to, and I was right. But since I had lots of slides on that, I decided to include them so that people can look at them. I think what the theorists do is they try to answer this question: how do neutrinos get a mass? The short answer is we don't know. Okay. Now, this is a good kind of we don't know as opposed to a bad kind of we don't know. It's we don't know, but we have lots of different ideas of how to give neutrinos a mass. And there are lots of them. And they all work. And we know this because there were a bunch of other ideas that didn't work. And we don't talk about those anymore. But there's still a whole bunch of them that work. So the real question is which one of these ideas is right? Maybe none of them are right, but chances are that one of them is at least qualitatively right, and we don't know which one is right. And in order to get the right answer, we need experiment. You know, we can theorize and philosophize as much as we want, and I can convince you that my favorite model is the right one, but you should not be convinced, because I would be lying. You need experimental data for that. So we need a lot more information in order to figure out which one is the right neutrino model. And I do want to say that this is a big campaign that involves a lot of experimental activities, many of which have absolutely nothing to do with neutrino physics. So you can inform this neutrino mass puzzle in a large variety of ways, that many of which have nothing to do with neutrino physics, which means if you want to be serious about learning how neutrinos get a mass, you have to learn a lot of particle physics, because the answer can come from lots of different places. Okay, so let me just jump to my last slide, so you can read all of this now. I'm going slowly enough. Oh, I didn't talk about flavor mixing, but I won't talk about flavor mixing. So just to conclude, this is the messages that are very important. We know the Standard Model is wrong because we discovered that neutrino masses are not zero. If you don't believe the dark matter problem, because that has to do with astrophysics and cosmology, and these things are very complicated, neutrino masses are enough evidence that the Standard Model is wrong. We still know very, very little about the physics responsible for non-zero neutrino masses, and we're going to require a lot of information. A couple of things which I said just now, or just one, is that we've learned that neutrino masses are really small. And we don't know why, but we think that's very important. So a lot of people spend a lot of time trying to answer that. One thing which I didn't talk about is that the neutrino mixing angles and the neutrino mixing and quark mixing are the same phenomenon, but quantitatively they are completely different. We don't know why that is, but we also don't know whether that's a good question to ask or not. Many people do ask that question, and a lot of research is related to understanding what those numbers mean, if you want to think about it that way. And I skipped my favorite solution to the problem. Orlando talked about this, so I didn't talk about this at all. We still have these short baseline anomalies. They might be indication that there's more to the neutrinos than meets the eye. And he talked about stereoneutrinos, but there could be other things going on. And the last thing I want to leave you with is something which is kind of a propaganda lie, but it's still nice. Actually, half of it is nice. The other one is true. The other one is a lie. One thing which is really fun about neutrinos is that you can understand a lot of the physics in very simple ways because it's basic quantum mechanics. And if you think about it that way, it is remarkable that we have this quantum mechanical system that is coherent, so that's what your quantum optics friends brag about all the time. And our quantum mechanical systems are coherent on the scales of 1,000 kilometers. Your quantum optics friends do not have lasers that are coherent at 1,000 kilometers. And we get ours almost for free because the neutrinos are produced in the atmosphere, for example. So we have this really long distance coherent quantum mechanical device. And as you know, quantum mechanical devices are really good at seeing things which are really, really hard to see because you can take advantage of interference. The example we like to give is that with our quantum mechanical device, we can see neutrino masses. And neutrino masses are really hard to see. Actually, that's the only way we ever got to see neutrino masses. All the other ways have failed miserably because the masses were so small. So oscillations are so powerful that they can see really tiny effects. And in principle, they give access to very, very high energy physics. So it is possible that the physics responsible for neutrino masses is at, say, 10 to the 14 GeV. And there's no other experiment other than perhaps proton decay searches that can access physics that's at 10 to the 14 GeV, just because the consequences of that at the experiments we can do are very small. But neutrino masses can do that through the power of neutrino oscillations. So it's always important to keep in mind that it is possible that by doing neutrino oscillation experiments, we can see more weird stuff that we didn't anticipate. And people do ask very bold questions like, do neutrinos violate Lorentz invariance by a little bit? And that could show up in neutrino oscillations. Another question you can ask is quantum mechanics right? Or is it modified in some weird but really tiny way? And again, neutrinos offer the ability to see very small effects because of the nature of neutrino oscillations as well. So it's a very powerful phenomenon that has the potential to do to change things in a qualitative way. So let me stop here. Thank you.
Hi. Neutrino oscillation can be lepton number violation sign or not?
That's a very good question. The answer is in principle, yes. Although you have to ask yourself if it really is neutrino oscillations or not. And the experiment that you would have in mind is the following. You know, I can produce a muon neutrino beam, and I can ask what's the probability that the muon neutrino beam will behave like an electron antineutrino. That's called a neutrino-antineutrino oscillations. Historically, by the way, this was the first model that was written down when people ran into the first, in quotes, evidence for neutrino oscillations, which turned out to be totally wrong for lots of reasons. But that was the first model that was written down. It's a totally crazy model. It makes no sense. But again, that was the model that was written down. And this was inspired by KK bar oscillations. So kaons and anti-kaons can oscillate into one another. And there's nothing wrong with that. Neutrino-antineutrino oscillations can also happen. But again, you can calculate an oscillation probability. And if you're very careful, you can also define the probability in a proper. So basically, the challenge is, remember I wrote down that PEE plus PE mu plus PE tau equals 1. That means the probability of producing a neutrino and measuring it as anything is 100%. Makes sense. But if the neutrino can be measured as an antineutrino, I have to have some addenda. I have to add other oscillation probabilities there, and I can probably do it in a self-consistent way. But the bottom line is, yes, you can look for this, but just like the double beta decay, the probability of that happen is proportional to the neutrino mass divided by the neutrino energy. So your oscillation probability has something that looks like a normal oscillation probability multiplied by m over e, which makes the probabilities really small. But yeah, there's this thing called neutrino-antineutrino oscillations. And you can do in paper all kinds of cute measurements, which are impossible to do in the real world. But if you could do it, it would be nice.
Okay, so let's thank again André. Thanks a lot. So this was his last talk of the course, but he again will be available later this afternoon to ask to answer more questions. Okay. So now we start with the poster madness, and I guess Eric is coming. No. Sorry about it. So, okay, great. Can you hear him? Yeah. That one.
Good afternoon. The name of my work is Contribution of Neutral Scalar Particles to Flavor Changing Neutral Currents in Gamma Decays. This work is based on the mass of the top quark. Allows us to study new physical effects such as flavor changing by neutral currents. And the principal motivation of this is that in the standard model, this decay is highly suppressed at the first level. It doesn't exist at 3 level, and it has a breaching ratio around 10 to the minus 12. Means it's not observable, but in my work, I found that breaching ratio of the order of 10 to the minus 6, a million times better than the standard model, but it's still unobservable. But it's better. We work with extended model with extra Higgs singlet as well as extra Higgs doublet. It allows to, it gives dark matter particles, scalar dark matter particles, and we use them to perform the breaching ratio. That's it.
You. And of course, you can see his poster during the coffee breaks. Now, you ask Rafaela. Eric? Okay. No, this one is the right one.
Hi guys, my name is Rafaela. I'm doing a master degree in physics at FBC. Poster, I will talk about the dry water of array. That is an experiment to measure high energy cosmic rays. I will describe this. Show some result of muons contour rates that code relativity in solar flare. So, thank you for attention. Welcome to.
Thank you. Javier Israel from University of Guanajuato.
Hi, my name is Javier. I come from the University of Guanajuato in Mexico, and I'm going to talk about a work that we did last year. It's about a prospect for indirect dark matter detection using gamma rays. We basically look at the galactic center and a dwarf spheroidal galaxy called Draco, and try to put constraints using the latest CMB data. And well, that's it. And you're welcome to come to my poster. Thank you.
Clara Watanabe from UFRJ. UFRG.
Oh, hi, my name is Clara. I'm from I'm a master student at Federal University of Rio de Janeiro, and I work at DAMIC collaboration. DAMIC is an international dark matter direct detection experiment that employs CCDs to search for low masses WIMPs. Low masses is below 20 GeV. And in my poster, I will present the experiment and show how the CCD works as a detector. Thank you.
Sure. Felix.
Well, hello everyone. My name is Felix Diaz. I am a PhD student at Pontificia Universidad Católica del Perú. And today I will present a poster. The title is Quantum Decoherence and CPT Violation at Dune. This work is being done in collaboration with Juan Carlos Carrasco and Alberto Gago. So, here we consider the neutrino like a quantum system that interacts with the environment. So due to this interaction with the environment, the neutrino lose coherence. So this phenomenon can modify the interference between the massing and the states. So and therefore we can, the oscillation probabilities can be altered. Well, we found some scenarios that don't respect the CPT symmetry. So here we develop some analytical expression for probability oscillation and for CPT asymmetry, and in vacuum. And for matter we do simulations using Nuskit and Globes. And in order to evaluate these CPT violation effects, we use NUMU and NUMU bar disappearance channels in the context of Dune experiment, where we know about it. So finally, we found 5 sigmas of confidence for our best case for different energy dependencies. If you want to know more about this work, you can ask me. The poster is right outside.
Thank you. And that was the last one. Okay, thanks. So now we break for lunch, and just to remind that we're back at 2:30 today.